This is video 4 for the mechanics unit. So in this one we're going to talk about mechanical advantage. Now remember that a machine is some sort of device that makes it possible to do more work conveniently by either increasing the speed of an operation or decreasing the force that you need to supply, or simply changing the direction of the force. So bicycles are a great example of this. Um, so here we have a bicycle, and it's a chain driven thing. So what we can do is we can take a look at the input distances, input forces, output distances, and output forces. So taking a look at the first one here, let's take a look at this lower gear. And what we're going to do first is we're going to calculate how much input work is being done. Now remember, work is a force times a distance, and the force needs to be parallel to the distance. So looking at this then, the input work would be 1,000 newtons times 0.15 meters. We need to convert centimeters into meters. And that gives me an input work of 150 joules. Over here we can calculate the output work. So that's going to be 440 newtons, 0.34 meters. And for the output work I get like 149.6. Very, very close. So notice then that machines do not reduce the amount of work you do. The input work equals the output work. So what exactly do machines do then if they don't reduce how much work we do? Well, again, they either make it easier to do the work or they make it more convenient. Or, maybe they do nothing except redirect the direction of the force. But it's important for you to realize that machines do not reduce the amount of work. Now, machines provide something called mechanical advantage that will make it easier for you to complete a task. So we take the output force and we divide it by the input force. So in our previous example, our output force was 440 newtons. Input force was 1,000 newtons. Now this gives us something that is less than 1. So when you get a mechanical advantage that's less than 1, it's a machine that is designed to make you go faster. It's not meant to, lift anything heavy, if you will. Also notice that the units disappear. Mechanical advantage is a ratio, and ratios have no units. Now torque is the rotational equivalent of force. So we can also write the mechanical advantage formula in terms of output torque divided by input torque. For gears, we use the number of teeth to help us calculate the mechanical advantage. Now we have non-compound gear trains and compound gear trains. So and really the formulas for both are the same. It's always output over input. So here we got the driving gear, and here we have the driven gear. The driving gear is always the input. The driven gear is always the output. So output over input. What I could do is take 30. I can do 60 divided by 36 times 36 divided by 12. Output over input. And the 36's cancel. So what this is a mechanical advantage of 12 or 60 over 12, which is 5. So something like this is set up for for, torque, to increase your torque. It is not set up for speed at all. So this little tiny 12-tooth gear is going to be spinning 5 times to make the big gear spin once. For the compound gears, again, it's just output divided by input. So here is our input, the driving gear. The driven gears are output. So here, it looks like it's 60 over 12 times. Now, since this little 12-tooth and this 60-tooth share the same axle, I can kind of ignore it a little bit. They're turning at the same rate. So I'd have another 60 over 12. 5 times 5 is 25. And again, that's set up for torque and not for speed. That driving gear needs to turn 25 times just to make the driven gear turn once. Now, once we have the mechanical advantage, we can use it in calculations. So for example, the output torque equals the mechanical advantage multiplied by the input torque. The output speed equals the input speed divided by mechanical advantage. So what we can get from this then is we can calculate angular speeds. And then remember, linear speed equals radius times angular speed. So once we know what that output speed is, we can multiply that by the radius of the tire, and that can calculate for us the linear speed of the robot. The next thing I want to talk about is efficiency. And basically, no machine is perfect. There's always some sort of friction, and it takes energy away from the system. And work is energy. So the way we calculate this is we take the output work and we divide it by the input work. And then once we have that, we multiply by 100 to turn it into a percentage. We usually represent this as a percentage. Notice that this is also a ratio, so it's going to be unitless. So in our previous example, we saw that the output work was 149.6 joules. The input work was 150 joules. So that bicycle do a quick calculation here, was 99.7% efficient. In other words, it only lost 0.3% of the energy due to friction. And that's pretty good. I mean, bicycles are usually pretty efficient. All right, now we need to talk about traction. This is the friction between the wheel and the surface that it rolls on. Friction opposes sliding, so we can take a look at 2 cases. One where the wheel is being powered, and the other where the wheel is not powered. Think of the front and back wheels on a bike. The back wheel is powered, the front wheel is not. So, I have a couple pictures here, but I think it's a little easier if I redraw this. So first off, we have the powered wheel. So let's say that it's being turned this way. So it's spinning this way, so there's a torque, rotating it counter or clockwise here. This wheel has a radius, and it's on a surface. So since there's a torque acting on it, there's going to be an applied force going that way. And that should make sense. If the wheel is turning clockwise, it's giving a force to the back. However, friction opposes sliding. Now this is going to be static friction, not kinetic. It becomes kinetic if you do a burnout. And then also we have a normal force and a gravity force. So if I were to do a little bit of math here, I can start to look at forces along their x and y axes. So when I study the forces along the y-axis, I get the normal force minus the gravity force, and that equals 0. They're in equilibrium. They cancel each other out. So the normal force equals the weight of wherever that tire is, or the weight placed on the tire. When I take a look at the forces on the x-axis, I have friction minus the traction, or that force. And if I want to get the maximum traction, these need to be 0. So the applied force needs to be just as strong as the friction force if I wish to have full traction. So this means then that the applied force must equal the friction force. Now the applied force, if you remember, torque is a force times a lever arm distance. So this applied force will be the torque divided by the radius of the wheel. Friction is coefficient times normal force. And we just figured out the normal force is mg. So there we have an equation for a wheel. So we know that the torque is, we can get that from the mechanical advantage and everything. We know what the radius of the wheel is. We should know how much weight is on it. And the trick comes to finding the coefficient. So that's a powered wheel. For a non-powered wheel, it's a little different. So let's say the wheel is spinning in this direction, clockwise once again. There is no power being applied to this wheel, but friction opposes sliding. So this time, the friction force is in that direction. So it's in the opposite direction that we'd expect for a powered wheel. Other than that, we just have our usual normal force and gravity force, and really that's it. It's not a whole lot to the non-powered wheel, which is kind of nice. All right, well, that concludes our mechanics unit.